Let's move on from Walker cell to the best known interannual mode of variability that arises off it as the convection moves, as we have seen. But first, let's do what would have something about what would happen if the ocean was actively interacting with the atmosphere during this heating and the large-scale divergent flow that was getting set up. So we had a heating here, and the lower level we had convergence over the heating and vertical motion, and we had off-equatorial circulations getting set up as seen by these geopotential anomalies extending all the way to the poles, right? So imagine that you had the ocean where, if we remember, we saw that the wind forcing creates the Ekman spiral, Ekman transports, and of course also the Ekman divergence, movement of the thermocline, and so on. So if you think briefly about westerly wind anomalies, for example, associated with the heating, then these are going to push the water towards the east, and if you add Coriolis to the right in the northern hemisphere, to the left in the southern hemisphere, then you have convergence into the equator, so you have thermocline being pushed, so the warm SST anomaly that is associated, or let's say the heating is in the atmosphere as we have prescribed, but this convergence is going to create a warm SST anomalies. On the other hand, on the eastern side, the easterlies are going to create asymmetric but Ekman divergence, upwelling, and colder SSTs. So the convection is going to move east because of these ocean interactions, okay, in a very first order sense. Of course, the full SST response is going to depend on the mixed layer heat budget, how the thermocline moves, how much kinetic energy there is in the winds, how much heat flux is being changed by the convection in terms of latent heat loss, radiation changes, and so on. But nonetheless, in to the first order, you can imagine that in the tropics, when you have such heating, it's pretty much guaranteed that the anomaly is not going to be stationary if it is a fully coupled system. So obviously there are other time scales involved, like waves being set off at different time scales, etc. But we can move on to combining these ideas into understanding the southern oscillation, El Niño and La Niña. We already talked about the southern oscillation in terms of the pressure oscillation between Tahiti and Darwin, both of which are south of the equator. And the idea of Walker had caught on by the 1950s and 60s. People were already beginning to find correlations between the southern oscillation and rainfall and temperatures at various places, but the correlation was not stationary. Some disappeared at some point, and people were kind of worried that maybe this is not such a good measure for forecasting. But Troop persevered and stated that the southern oscillation has intrinsic interest as a complex of interactions over a very large area. We already talked about the global teleconnections associated with this large-scale mass exchange between the western and eastern hemispheres. And moreover, there is a premise of its use in seasonal forecasting or foreshadowing, and it may be said that some regions affected by it are those most favored for success in this field. Hence, increased understanding of its nature and mode of operation should have valuable practical results. This was almost a decade before Bjerknes came along and figured out that there is a positive feedback between the atmosphere and the ocean. Looking at the seasonal correlations of Darwin mean sea level pressure with mean sea level pressure everywhere. So you take Darwin as the base point and you correlate every point on the planet. Obviously correlation is high locally and falls off and changes sign as you get towards Haiti, and there are these large scale patterns as well. And you can see that even in June, July, August, the correlation of Darwin only covers part of India as far as high correlations are concerned, which may give us a sense that El Nino effect on India is not going to be uniform, even considering that Southern Oscillation is not the complete El Nino story, that there are other heating movements involved and Rossby waves in the atmosphere and so on are involved. Nonetheless, you can clearly see the movement of the correlation. So with the movement of the ITCZ and the heating, you're going to change the correlation. So you can see the waxing and waning of this center as well as the changes in this center. So that's for JJ and SON. So that's the idea of correlations of Southern Oscillation, which is the difference of these two pressure centers. So Tahiti minus Darwin, this is high, this is low, that's positive, but during an El Nino this becomes anomalously low and this becomes anomalously high. You have negative anomalies. So the correlations are global, so there are many places where data showed going back in time. So oops, I misplaced the oh, there it is. So this is the data that was being used in these plots. So you have Honolulu, Canton, Tahiti's, oops, Tahiti is there, Line Islands over there, what else do we need? Lima, Peru is over here, and so on. So the data from these sites is being used here to look at delta SST, which shows that the between the centers there is always interannual oscillation, so no year is really zero, and this is from these boxes in the deep tropical Pacific, and this is the rainfall over Puerto Chima in Peru, then Santiago and Darwin delta P, Easter Island and Darwin delta P. You can see high correlations between them. Strength of the south equatorial current, because when the Southern Oscillation changed, the winds changed and the equatorial ocean currents changed, advection of heat would change, that would change sea surface temperatures, and that could have positive feedback on the Southern Oscillation. Zonal winds at Canton Island, a 200 hectopascal and 850 hectopascal. You can see the basically out of phase relation at low and high levels. Trade convergence and Line Island precipitation index, again there is a high correlation. Meridional winds converging into, so Line Island is here, so winds are coming in the south easterly winds all the way here, so the cross-equatorial convergence is going to influence, is going to be correlated with rainfall over Line Islands. This, historically speaking, this is good data that actually increased awareness and was used by Troop and others to conclude many thoughts and make advances, but obviously now we can have lots of recompiled, reprocessed, reanalysis data which allow us to do such long time scale continuous analysis, where the wavelet analysis is being done here, where you are looking at periods changing from annual to multi-decadal, and you are looking at the 2 to 8 year bandpass filtered and interannual sea surface temperature anomalies in the Niño 3.4 SST area, which is 5 north, 5 south, and 170 west to 120 west. So it is central western Pacific to the eastern Pacific, just east of Galapagos. Basically, it shows that there are times when the annual cycle is fairly strong, and there are times when there is the quasi-quadrennial time scale of El Nino that's pretty strong, but then it completely weakened over here. There are also decadal time scales. These are kind of significance lines here that you need to learn to interpret wavelet analysis. And the El Nino variability at this times interannual time scales reappears here with a mix of quasi-biennial and quasi-quadrennial time scales. So obviously the Southern Oscillation and the Niño 3 SST have rich spectrum of time scales that are not stationary. So in time, the variance at various time scales changes, and hence their correlation with various fields far away in remote places, which could be forecasted based on Southern Oscillation, also begin to have waxing and waning correlations. So wavelets power spectrum using the Morlet wavelet of the Niño 3.4 SST is shown here. This shows evolving wavelet amplitude as a function of time from 1871 to 1996, which ends here. Shaded contours indicate statistical significance, with solid black contours indicating greater than 95% confidence. Cross-hatched areas indicate cone of influence where zero padding has reduced the variance. So to do the variance, you need to deal with the ends of the time series to get the time scale. So zero padding is done there, which affects the variance. Lower panel shows time series of Niño 3.4 SST with the red contour indicating a 20-year running average with variance in the 2 to 8 year period band. Okay, so panel to the right indicates the average spectra of over the entire period computed by the fast Fourier transform of the entire data set and summed wavelet modulus. Okay, the solid curve on the periogram indicates 95% statistical significance. So this is showing significance. And the book just makes a statement that just using fast Fourier transforms, you don't get this kind of information that wavelets give you, which is the changing spectral power in various period bands that change over time. So there is additional information that tells you how El Niño evolution can be looked at on interannual time scales, and also its variance, which sometimes is referred to as ENSO variability. So how ENSO itself is varying from one decade to another decade, or from some decades to other decades, using wavelet analysis. Okay, maybe I'll come to this in the next podcast to look at how El Niño variance over time can be looked at, even just using the Niño 3 or Niño 3.4 SST anomaly index. The evolution of these indices has happened over time, and it was originally 2 coastal boxes, 1 eastern box and 1 western box, and then over time the box was moved a little to the central eastern region to capture better the El Niño and its variance over time.